Area of a segment of a circle. Hello everyone. Before we dive into today's new topic, let's take a quick moment to reflect on what we have already covered. In our previous lessons, we explored how to calculate the area of a sector. You can visualize a sector as that classic, pie-slice, shaped region that extends from the center of the circle out to the edge. Now, building on that foundation, we are going to shift our focus to a different, specific part of the circle known as the segment. In the next few slides, I will show you exactly how to identify this region and, more importantly, how to calculate its area. Conceptual understanding. Now that we've refreshed our memory on what a sector looks like, let's move on to slide 2 to build our conceptual understanding of the segment. First, let's define what we are actually looking at. A segment is simply the region of a circle that is bounded by a chord and its corresponding arc. To make this easier to visualize, I want you to imagine you are holding a circular piece of paper. If you take a ruler and draw a chord, which is just a straight line connecting any 2 points on the edge of your circle, you will notice that the circle is now divided into 2 distinct parts. The smaller of these 2 parts is what we call the minor segment. Now, you might be wondering, how do we actually calculate the area of this small piece? The most intuitive way to approach this is to realize that the segment is actually a part of the sector we studied in the previous lesson. Think of it this way: if you take a full sector, that classic pie-slice shape, and you cut off the triangle formed by the 2 radii and the chord, the piece of paper you have left over is the segment. Because of this, the logic for our calculation is based entirely on subtraction. As you can see on the slide, the area of the segment equals the area of the sector minus the area of the triangle. Keep this subtraction logic in mind, because in the next slide, we are going to break this down into a formal, step-by-step derivation of the formula. Step-by-step derivation of the formula. Now that we have a conceptual grasp of what a segment actually is, remembering that it's just the leftover part after we remove a triangle from a sector, let's break down the mathematical process into a clear, step-by-step derivation. This will give you a reliable roadmap for solving any problem of this type. Step 1. We begin by calculating the area of the sector. Specifically, we want to find the area of the sector, labeled OAPB, which is the larger pie slice that contains our segment. To do this, we use the standard formula for the area of a sector, which is theta divided by 360 multiplied by pi r squared, where theta represents our central angle and r is the radius of the circle. Step 2. Next, we need to find the area of the triangle. If you look at the chord we discussed in the previous slide, you'll see it forms a triangle labeled delta OAB, with the center of the circle, point O, and the 2 endpoints of the chord, A and B depending on the information given in your problem. You can find this area using the traditional base and height method. Or, if you are working with non-right-angled triangles, you can use the trigonometric methods we covered in our previous lesson. Step 3. This is the most crucial part of the logic. To isolate the area of the minor segment, labeled APB, we simply subtract the area of the triangle from the area of the sector. In mathematical terms, the area of segment APB equals the area of sector OAPB minus the area of triangle OAB. When we put all of this together, we arrive at our final combined formula. The area of the segment is equal to the quantity theta divided by 360 multiplied by pi r squared, minus the area of triangle OAB. Keep this formula in mind, because in the next slide, we are going to apply this exact logic to a real-world architectural example. Real-world example. Now that we have understood the theory and the formula behind the segment, let's put it into practice with a real-world application. Imagine you are looking at a circular architectural window. This window has a radius of 14 centimeters. A decorative metal cord is placed across the window, and this cord subtend an angle of 90 degrees at the center of the circle. Our task is to find the area of the minor segment created by this cord. For our calculations, we will use 22/7 as the value for pi. let's break this down into a step-by-step solution. First, let's clearly identify what we are given. The radius, r, is 14 centimeters, and the central angle, theta, is 90 degrees. Step 1, we need to find the area of the sector. To do this, we use the formula we discussed in the previous slides. Theta divided by 360 multiplied by pi r squared. Plugging in our values, we get 90 divided by 360 multiplied by 22/7 times 14 times 14. If we simplify 90 over 360, we get 1/4. When we multiply 22/7 by 14, one of the 14s cancels out the 7, leaving us with 22 times 2. So, our equation becomes 1/4, multiplied by 22, multiplied by 2, multiplied by 14. This simplifies further to 1/4, multiplied by 616, which gives us an area of 154 square centimeters for the sector. Step 2, next we need to find the area of the triangle OAB. Because our central angle is exactly 90 degrees, we are dealing with a right-angled triangle where both the base and the height are equal to the radius, which is 14 centimeters. Using the standard formula for the area of a triangle, which is 1/2 multiplied by base multiplied by height, we calculate 1/2 times 14 times 14. This simplifies to 7 times 14, resulting in an area of 98 square centimeters for the triangle. Step 3, finally, we apply the subtraction logic we learned earlier. To find the area of the segment, we subtract the area of the triangle from the area of the sector. So, 154 minus 98 gives us a final result of 56 square centimeters. As we move to the next slide, I want you to pay close attention, because I will highlight some common pitfalls where students often lose marks in problems exactly like this one. Common mistakes to avoid. First, a very common mistake is confusing the sector with the segment. It is easy to accidentally use the sector formula and stop there. To keep them straight in your mind, try this visualization. Think of a sector as a full slice of pizza, which includes the pointy part at the center. A segment, however, is more like just the crust piece at the edge, which excludes that center point. Always ask yourself, am I looking for the whole slice or just the edge? Second, pay close attention to how you calculate the area of the triangle OAB in the example we just worked through. The angle was 90 degrees, which allowed us to use the simple formula of 1/2 times radius. However, do not assume every triangle is right-angled. If the central angle is anything other than 90 degrees, you cannot simply use that method. You must be prepared to use trigonometry, or the base and height method, to find the area of that triangle accurately. Finally, watch out for calculation errors involving pi. Before you start your final calculation, always check the instructions. Does the question ask you to leave your answer in terms of pi, or does it specify a value like 3.14 or 22/7? Using the wrong value for pi can lead to an incorrect final result. Now that we have seen how to solve a practical problem, I want to pause and discuss some common pitfalls. Even if you understand the concept, it is very easy to lose marks due to small errors. Keep these points in mind, and you will be well prepared for the final summary of this topic. Key takeaways. First, let's reinforce our definition. Remember that a segment is simply that specific region of a circle trapped between a chord and its corresponding arc. As we worked through our step-by-step derivation and our window example earlier, the most important strategy to remember is this. The area of a minor segment is always found by taking the area of the corresponding sector and subtracting the area of the triangle formed by the radii and the chord. To put this into a single mathematical rule, here is your formula summary. The area of a segment equals theta over 360 multiplied by pi r squared minus the area of triangle OAB. Finally, a word of caution as you approach your exam problems. The accuracy of your final segment area depends entirely on how precisely you calculate those two individual parts. If your sector area or your triangle area is off, your final answer will be 2. So, always double-check your trigonometry and your arithmetic. All right, we have reached the end of our lesson, so let's wrap everything up with some key takeaways to ensure you've mastered this concept. Great job today, keep practicing these subtractions, and you'll master this in no time.